Madison College Building Construction for the Fire Service, Week 5, Homework Problem 2. This problem is very similar to Homework Problem 1. The only difference is that in Problem 1 we made an assumption that the beam was weightless, which is a common assumption in structural engineering because relative to the load supported by the beam's own weight, that is to say the dead load, is small compared to the live load, the things that are placed on the beam. In this case, we were to assume that the beam does have a weight of 100 pounds, and it is it's uniformly distributed. So if we were going to draw it, we could draw it as a whole field of these short little vectors over its entire length. It's spread out all across the beam. But the upshot is that in that situation, we can consider it to purely act right at the center with a weight of 100 pounds. 50 pounds on either side, uniformly distributed, is just like it acts at the center. Now, where is this relative in the length of the beam? Well, the beam is 12 feet long, so this 100-pound weight is 6 feet from the end. And again, this is very similar to a problem you saw in the previous chapter. This is a review exercise. We will solve this problem using a similar technique. However, I'm going to use my location of my pivot here. This will be the fulcrum for all of our moment calculations on the opposite end of the beam, just to show that the calculation does work either direction. Again, in this case, we have the weight of each painter, which is, I believe, negative 180 pounds per painter, and that was taken actually from problem number 1. So again, the technique to solving basically any of these statics problems, we start looking at the sum of the forces. Well, the sum of the forces in the x direction, there are no forces in the x direction, so that becomes rather straightforward. The sum of the forces in the y direction equals the weight of the painter plus the weight of the other painter plus the weight of the beam plus the tension in these wire ropes, and again I will label this as T sub AB for tension in wire rope from point A to point B. This is T sub EF for the tension in wire rope E to the F. And T to the EF. And all of those have to add to 0 for this to be in static equilibrium. Now we can't solve that problem as it is because it's got 2 variables, so now we are going to generate the sum of the moments. And again, this is a bit lengthier statement, so I'll come down where we've got a little bit more room. The sum of the moments, and in this case it's going to be about point E, equals, well, the painter has a weight of 180. Remember, it's a negative number because the force is in the negative y direction, times a displacement of negative 4 feet because he's or she is 4 feet left of the fulcrum, plus the weight of the beam, that has a weight of negative 100, times a displacement of negative 6 feet because it's to the left of the fulcrum, plus a weight of 180 times a distance of, let's see, 10 feet from point E, plus the tension in wire rope AB, which is at a distance of 12 feet. And again, the sum of the moments must be 0. So now it's just a matter of turning the crank on this. Let's see, 4 times 180, that's 400 plus 320, so 720, and it's 2 negatives, so it's positive 720. Negative 6 times negative 100, that's 600. Negative 180 times negative 10, that's plus 1800. So if you think about all of these forces, they tend to create a positive rotation about point E. And remember that positive rotation is counterclockwise. And that makes sense. If you were to cut wire rope AB, this whole plank is going to swing in this clockwise direction. Plus 12 feet times the tension in wire rope AB. Now, the process of pushing this all around, I'm going to subtract all of this stuff from one side, and I'm going to divide both sides by 12 to get tension AB by itself. So the tension in wire rope AB equals 720 plus 600 plus 1800, and it will be a negative number in this case. And this distance is actually a negative distance. So it's all of this divided by negative 12. Let's see, 600 and 1800, that's 2400, and another 720 is 3120. And again, because I've switched sides of the equal sign, it becomes negative. And taking the quotient of those two numbers, and I can take them both as positive because a negative divided by a negative is a negative. And we get the tension in wire rope AB as 260 pounds, which agrees with the answer given in the answer key. Now, tension in wire rope EF, well, what do we know? One of the things we know is that basically the sum of the tensions in the two wire ropes, that is to say tension AB plus tension EF, must equal the opposite of all these weights. So if we think about these weights, we have 180 and 180 is 360, and another 100 is 460. From that 460, we subtract out the tension in wire rope AB, which is 260, and what remains for tension for wire rope E is 200 pounds. Just to verify that, we could rerun the calculation, now making point B the fulcrum. So we look at the sum of the moments about point B. Now in this case, positive 2 feet times negative 180 plus positive 10 feet times negative 100 plus positive, let's see, where is this person D? 8 feet. I'm sorry, this is not correct. This should be 6 feet times. Should be 6 feet times 100, not 10 feet. Position D is 8 feet. Positive 8 feet times negative 180. And then the wire rope EF is positive 12 feet times the tension in wire rope EF. And again, these all need to add to 0. Turning the crank, we get negative 360 plus negative 600. Let's write those down. Plus 8 times negative 180. Well, 8 times negative 100 is negative 800, plus another negative 640, negative 1640, plus 12 times the tension in wire rope EF. And of course, these are all negative moments because if we were to cut wire rope EF, this thing's going to want to pivot in a clockwise direction, which in the Cartesian plane is considered a negative rotation, whereas a counterclockwise rotation would be considered positive. So let's move them all to the other side of the equation. We have 360 and 600. That's 960. 960 plus 1640. Well, 960 plus 40 is 1,000, plus 1,600 more is 2,600. So 2,600 foot-pounds, and we'll divide both sides by 12, equals the tension in wire rope EF. Now, I can tell right now that there's an error in here because this ratio should be 200 pounds. So let's go check the math. 800 plus 640, here it is. It's not 1640, it's 1440. Okay, so that changing that makes this 2,400 pounds. 2,400 divided by 12 feet, 2,400 foot-pounds divided by 12 feet results in a weight or a tension of 200 pounds. So everything checks out. We match the answer key and we match our own internal check of the rationality of the result.